What we're going to do is we're going to go over the concept of isotopes. And first what we'll do is we'll look at the theory, and then we'll look at how they play out in determining the average mass of an element. Now, to understand the theory of an isotope, we have to review some of what we know about the history of an atom. We remember that we start off with Dalton, and he had his billiard ball model of the atom. And it was the first atomic model because it reintroduced the concept of an atom. And he had his main points, where elements are extremely small particles. The atom of each type is different from the atoms of other types of elements. They cannot be created or destroyed. They combine and are rearranged. Following that, we had Thomson, who, using a cathode ray tube, developed the plum pudding model. Through the application of this piece of technology, he was able to show the presence of the electron. And he postulated that it was embedded in a sea of positive material, and so that's why he called his model the plum pudding model. Okay. And he stated that the atom was neutral with the negative particles embedded in a positive material. Then we had Rutherford, who had a nuclear model. He set out to show that Thomson's model was correct, and he did the gold foil experiment. And in the gold foil experiment, he fired alpha particles, which were produced through the radioactive decay of radium, at a thin layer of gold, and he found that some were deflected and reflected. And so it resulted in him postulating that most of the atom was empty space, with most of the mass and all the positive material in a dense core that had a positive charge, and the electrons are around, and he coined the term proton. Bohr, who worked out of Thomson's lab and was a compatriot of him, developed his planetary model using the results of a variety of different experiments that researchers around Europe at the time were making. He came up with what we know the planetary model, where electrons are in orbits around the nucleus, with each orbit holding a specific number of electrons, but the key being that he said that electrons have specific energy, which allows them to maintain their position. And this helped to overcome the difficulties with Rutherford's model. And he talked about why the emission and absorption spectrums of atoms would be created due to the movement of electrons between orbits. After that, we had a bit of a break, and Rutherford, while working in his lab, working with a variety of other researchers, finally resulted in Chadwick being accredited with discovering the neutron. And so the neutron was able to help account for the missing mass that Rutherford thought that the proton couldn't account for, and was shown to have a neutral charge. Now, the neutron is of particular importance for us in terms of an isotope, because what they found that some atoms had the same number of protons but had different masses. So for example, here in the diagram I'm showing you, I have 3 examples of a hydrogen atom. In the first one, my hydrogen has 1 proton, denoted by the blue circle, and 1 electron, denoted by the red circle. In the second one, it has 1 proton and 1 neutron in the center in the nucleus. And in the third, it has 1 proton and 2 neutrons. What's key here is that we can see that the number of protons doesn't change, so we know that this is a hydrogen atom, but the number of neutrons do. And since the number of neutrons do change, it changes the mass of the atom. Since they're all hydrogen atoms, due to the 1 proton, we call them isotopes of each other. Now, we have what we call our standard notation, which allows us to denote or state the amount of protons and neutrons in a given atom. And so we have what we call our atomic number, which is the number of protons, and then our atomic mass, which is the sum of the protons and the neutrons. Because as you remember, a proton and a neutron had the same mass. So here's our standard notation, where we can see that we write the symbol, and as a subscript to the left we write its atomic number, and as a superscript to the left we write its atomic mass. So here for our 3 hydrogen atoms we can write the standard notation for its 3 isotopes, and we can see the changing number, and we can then tell that in the first one, if we do 1 minus 1, that's 0, so there's no neutrons. 2 minus 1, which is 1, so there's 1 neutron. 3 minus 1, which is 2, so there's 2 neutrons. Now, because of the mass of a proton and a neutron is so tiny, it results in the mass of an individual atom being extremely small. And so as a result, we have a special unit for measuring the mass of individual atoms, which we call our atomic mass unit. And because they have the same mass, we stated that the mass of a proton or neutron would have a mass of 1. So therefore, an atom with 3 protons and 3 neutrons would have an atomic mass of 6. But if we look on the periodic table, what we see is that the masses of the atoms given all have decimal values. And this is because it's a weighted average. Although atoms can have isotopes, the isotopes don't all appear in nature in the same amount. And so we take into account the amount that each isotope is found in a sample of an element to determine its mass. And so to determine a weighted average, what we do is we take the isotope's abundance and we multiply by its mass and we add them up.